Hey everyone, welcome to The Explainer. Today we're looking at one of the most elegant, powerful, and frankly magical imaging tools in modern medicine, magnetic resonance imaging, or MRI. As biomedical engineering students, getting a solid grip on this technology is absolutely foundational. We're going to explore exactly how we can build a highly detailed, three-dimensional image of the human body without using a single drop of ionizing radiation or making any surgical incisions. It is just pure, brilliant physics. Let's get into it.
Okay, pause and just think about this number for a second. If you hold just 3 liters of water, you're holding roughly 10 trillion hydrogen atoms. It is a completely mind-boggling number. And what's so incredible here is that every single one of those hydrogen protons has a quantum mechanical spin. This means each one acts exactly like a tiny microscopic compass needle. They're just sitting there, waiting in the body to be harnessed by the MRI scanner so we can make them all sing in unison.
So, let's dive into our roadmap for today. First, the magnetic symphony. Second, flipping the protons. Third, creating image contrast. Fourth, mapping the invisible data. And finally, engineering the scanner.
Section 1. The magnetic symphony, aligning those microscopic compass needles.
Our journey really kicks off the moment a patient enters the massive static magnetic field of the scanner. We call this the B0 field. Now, hydrogen is absolutely the star of the show in MRI. It's incredibly abundant in the human body, mostly in our water and fat, and because it has a quantum mechanical spin of 1/2, it acts as a microscopic bar magnet. Normally, out in the real world, these little proton magnets point in totally random directions, so their magnetic fields just cancel each other out. After all, Earth's magnetic field is a tiny 50 microtesla. But inside a clinical MRI scanner operating at 1.5 to 3 Tesla, that field is tens of thousands of times stronger. Inside that B0 field, these protons literally snap into alignment. Now, some will point with the field and some against it, but a very slight excess favors the lower energy parallel state. When you're dealing with 10 trillion protons, that slight excess, which is about 4.8 million per cubic millimeter, is more than enough to create a measurable net magnetization.
But here's the thing. These aligned protons, they don't just sit perfectly still. They precess. That means they wobble around the magnetic field axis, exactly like a spinning top wobbling under the force of gravity. And the exact speed of that wobble? Well, that's determined by the Larmor equation, omega equals gamma times B0. You can think of this as the central magic spell of MRI. Omega is our angular precession frequency, gamma is a constant that's completely unique to the hydrogen nucleus, and B0 is the strength of our main magnet.
To ground that abstract math into everyday physics, let's look at this number, 63.87. At a magnetic field strength of exactly 1.5 Tesla, hydrogen protons precess at 63.87 megahertz. Why does that actually matter to us? Because that frequency sits squarely in the FM radio band. MRI is, at its absolute core, a radio frequency technology. And if we were to double the magnet strength up to 3 Tesla, that precession frequency doubles right along with it to about 128 megahertz.
Section 2. Flipping the protons. The critical role of the radio frequency, or RF pulse.
So now that we have our protons aligned and wobbling at their Larmor frequency, we run into a major engineering problem. How do we detect a microscopic magnetic signal when it's completely drowned out by the scanner's enormous static B0 field? The short answer is, we can't. Not while it's parallel to that main field anyway. We absolutely have to tip that magnetization vector away from the main axis so our coils can actually pick it up.
And here's exactly how we pull that off. Step 1. We transmit a secondary oscillating magnetic field called the B1 field, also known as the RF pulse. We blast this at the precise Larmor frequency. When we do that, resonance occurs. It's exactly like pushing a kid on a swing at the perfect moment to transfer energy as efficiently as possible. Step 2. Thanks to that resonance, the protons absorb the energy and tip over. Let's say we tip them exactly 90 degrees into the transverse plane. Step 3. Once we switch off that RF pulse, this transverse magnetic vector keeps on precessing, basically acting like a spinning magnet. According to Faraday's law of induction, this rotating magnetic field cuts through our receive coils and induces a voltage. That tiny, decaying sinusoidal voltage, that is our initial MRI signal, which we call the free induction decay.
Section 3. Creating image contrast. Why different tissues look different in an MRI.
All right, so we've successfully got a signal. But those protons don't just stay tipped over forever. As they return to their comfortable equilibrium, 2 totally distinct relaxation processes happen at the exact same time.
First up, we have T1 relaxation, or spin lattice relaxation. This is the process of the longitudinal magnetization recovering as energy is transferred from the spinning protons to their surrounding molecular structure, the lattice. Second, we have T2 relaxation, or spin-spin relaxation. This describes the transverse magnetization decaying away. Why? Because the protons start experiencing slightly different local magnetic fields from their neighbors, meaning they very quickly lose phase coherence and fall completely out of step with one another.
Now, what's really fascinating here is how this translates to medicine. Look at these relaxation times at 1.5 Tesla. Tissues with tightly bound molecules, like fat, have very short T1 times, around 250 to 300 milliseconds. They recover their energy super rapidly. But look at a fluid like cerebrospinal fluid, or CSF. Its molecules are spaced far apart, so its T1 recovery is incredibly slow, taking up to 4,000 milliseconds. T2 decay times vary right alongside them. By programming our scanner to emphasize either T1 or T2 relaxation, we're exploiting these exact biological differences. This is what allows radiologists to clearly spot things like inflammation or tumors, because those conditions increase local water content and dramatically alter these relaxation times.
Section 4. Mapping the invisible data, gradients, and the mathematical magic of K-space.
So we've got our contrast, we've got our signal, but we still have one massive hurdle left. We have a strong radio signal hitting our coils. But where exactly in the body is it coming from? Right now, the signal is just one big, chaotic chorus of frequencies from the whole area. We need to isolate the exact physical location of every single drop of water. And that brings us to the wonderfully complex, mathematical magic of spatial encoding.
To map all of this in 3D, we use 3 sets of gradient coils to alter the main magnetic field in a perfectly linear way. This ensures that a signal's frequency and phase are completely dependent on its physical position. Let's break it down. Step 1 is slice selection using the GZ gradient. By varying the magnetic field from head to foot, an RF pulse of a very specific frequency will only excite protons in one specific slice of the body. Step 2 is frequency encoding with the GX gradient. We turn this on while reading the signal, so each vertical column of protons sings at a slightly different pitch, or frequency. Finally, step 3 is phase encoding using the GY gradient. We apply a brief pulse right before reading the signal to give each horizontal row a unique phase shift. Put it all together, and frequency plus phase uniquely identifies every single voxel in that anatomical slice.
All of that incredibly precise, carefully encoded data gets dumped into a two-dimensional mathematical grid called K-space. This is our raw MRI data. It looks like static, but it's brilliant. The center of this grid holds all the low spatial frequencies. That dictates your overall image contrast and brightness. The outer edges hold the high spatial frequencies, giving us those sharp edges and fine structural details. Finally, the scanner's computers apply a 2D Fourier transform to this grid, elegantly taking this invisible ocean of raw frequencies and phases and calculating the stunning, high-resolution diagnostic images that doctors rely on every single day.
Section 5. Engineering the scanner, extreme hardware, and strict safety protocols. To actually orchestrate this physics symphony, we have to zoom out to the macro level. This number right here, 4, it is absolutely critical. 4 Kelvin, which translates to negative 269 degrees Celsius. That is the temperature of the liquid helium used in the cryogen system to cool the main magnet. This B0 magnet is typically a massive solenoid made of niobium titanium filament. By cooling it all the way down to 4 Kelvin, the metal becomes completely superconducting. That means it can maintain that massive magnetic field indefinitely, with absolutely zero electrical resistance.
The real engineering marvel is how all these extreme components work together in total unison. We have the superconducting main magnet generating that massive B0 field. Nestled inside that, we have the gradient coils. Remember those spatial encoding steps we just talked about? Well, these gradient coils are physically switching on and off thousands of times per second to encode that spatial data. That rapid, violent switching is exactly what causes those incredibly loud, knocking sounds patients hear during a scan. Then we have the phased array RF coils, which act as antennas placed right up close to the anatomy to transmit the RF pulse and listen for that delicate returning signal. And of course, the cryogen system keeping the whole main magnet perfectly, continuously cooled.
Now, because these magnets are literally always on and incredibly powerful, safety is absolutely paramount. And that brings us to the number 5, specifically the 5 Gauss line. This is the critical safety boundary inside any MRI suite. Once you cross that 5 Gauss line, the magnetic field significantly exceeds Earth's normal background level.
Inside this zone, any ferromagnetic object, a pair of scissors, an oxygen tank, even certain medical implants like older pacemakers, can suddenly become a lethal high-speed projectile. This is exactly why strict safety protocols and rigorous patient screening are entirely non-negotiable before anyone even steps foot into that room.
So let's bring it all together. MRI is, without a doubt, a total symphony of magnetism, resonance, signal processing, and computational mathematics. For all the biomedical engineering students watching, understanding this beautiful, complex chain of physics is your fundamental building block. Really grasping how quantum spins turn into digital case-based data is your foundation for driving the next wave of clinical innovation. Whether you end up designing better coils, writing faster reconstruction algorithms, or optimizing new imaging sequences, this is where it all starts.
Which leaves us with a pretty exciting question to chew on. As we continue to push the boundaries of this technology, moving from standard 3 Tesla machines to ultra-high field 7 Tesla scanners that can actually resolve individual cortical layers in the human brain, what invisible secrets of the body will biomedical engineers decode next? It is a thrilling frontier for sure. Thank you so much for joining me for this explainer on the magic and physics of MRI. Be sure to check out our next explainer where we'll be breaking down how CT scanners work, moving from simple X-rays to full cross-sections. Keep curious, keep engineering, and I'll catch you next time.